Swayam Prabha. Digital India. Educated India.
Good morning everybody and welcome to our course on Introduction to Mechanical Micromachining. In the last class we have started with scaling law effect and we have seen that how different parameters behave or affect a system at different scale when you scale down one system from very higher scale to the lower scale. And we have seen some of the examples of different parameter like a surface to volume ratio and weight to surface tension. And let us see some more examples in the same way for the different parameter settings. So, now in the last class we have seen this example that what will happen when the surface tension will be more compared to the weight in this different scale. Now, there is one more effect related to weight scale of the surface area. At microscopic, the weight of an object is predominant and it falls down under the influence of the gravity. Now, if you see this particular example, that suppose a man or a human being is falling down from the top. So, what are the forces acting on that? One is the weight which will pull it down, that is considered as mg. So, this mg and this mg, m is the parameter which will be affected as a L cube because it is the mass of that part. And there is a drag force which is moving something in the upward, that is called air resistance. It will allow this person to move up and up, that means it will resist the free fall down of the part. So, that is given by the 1 up C rho A V square, and that is proportional to L cube. Now, if you see drag coefficient is the C, air density is velocity is, then frontal area is this part. So, this area is proportional to the L square, right. So, here if you see the weight is scaling as a L cube and the drag is scaling as a L square. That means, the things which is pulling down the person, it is scaling as a L cube, and things which is pushing this person in upward direction, it is scaling as a L square. Now, what will happen in this case? Now, see the when microscopic scale, when the same object becomes relatively insignificant compared to air resistance. Now, consider, let us take the example of an ant. Now, if you are putting this ant from a 1 floor or the 100 meter or consider even 1 hundreds of meter, then nothing is going to happen. When it is reaching to the bottom, it will actually go very freely, but same thing will not happen to the man when something is falling down from a large scale. Now, what is difference? Because if you consider here, difference is the weight. If you see weight of a ant is considered as a very small compared to the size. Now, considering the size, now this is the size of a L cube and this one particular thing, whole volume is a one particular part. So, let us consider this is a 1000. So, it will be scale as a L equal to 10, and now same thing will happen L equal to 0.1, then everything will scale down very small part here. So, if you put this particular parameter L equal to 0.1 and L equal to 10 in this particular part weight and the drag force, you can consider the weight will reduce very drastically, because this particular thing L cube will be 1000 and this thing will be the 0.001 in this case, that is in terms of the L cube. So, what is going to happen? The weight is reducing very fast, but drag is not reducing that fast. So, comparatively drag is very large compared to the weight which is pulling down this particular object from the bottom. So, that is the reason that when very heavy things will falling down from the bottom, then it will go very quickly, but when the lightweight things which is falling down from the same height or the even more than that, it will not reach with the same velocity or it will not get the same amount of resistance or same amount of gravitational force when it is moving down. So, that is the important thing, the small object becomes relatively insignificant compared to the resistance which is considered as a drag force. So, this thing is important role that we will see some of the things in the spindle design, that what is going to happen when your spindle is overhang for a longer time. Now, coming to the strength to weight ratio. Now, this is also important. Now, consider the critical buckling strength of a angular column ignoring the end condition. Now, this is one particular example here we have seen. So, this whole weight, it is taken care or it is loaded or it is mounted on the one particular column. It has a B, B and L is the length of that particular column. So, let us see what is going to happen in this case. Now, critical buckling strength is given by pi square E I into divided by L square. What are these parameters? E is the Young's modulus, but it has no connection with the length scale. I has a sectional modulus, so it has connection because here both things are B and B, it does not have the any different dimension, so it will be B raised to 4 by 12. So, if you put those things here, so now what is going to come here, that you keep the pi square as it is, E is not changing here, you put I equal to B square by 12 and L square is also dimension of this particular part. So, now we have a 2 dimensions. So, this is also length scale and this is also length scale, but in our B square is on the top and L square is at down. So, this will become 2 and this whole equation will behave as a L square in terms of dimension. And we know weight is considered as mg, where m is the one of the parameter which has connection with the length scale and it will behave as a L raised to cube. Now, what is going to happen in this case, when dimension of the column and weight shrinks linearly, that we are considering both the thing, because this is connected with the weight and this is connected with the dimension. So, if you consider only length scale, not considering any other than that, you reduce the L. If you reduce the L, mg will reduce, and when you reduce the L, your this whole parameter will change. Now, what is going to happen, that strength to weight ratio, now strength is scaling as a L square and weight is scaling as a L raised to cube. The whole thing will scale as a L raised to minus 1. So, what is important thing here? So, you reduce the scale here. So, all the weight will reduce as a L raised to cube. So, if you are 1 kg you are reducing to the 0.1, that means it will go very drastically in terms of the weight, but the strength is not reducing such a fast rate, it is L raised to square only. So, what is advantage here? So, for a 100 times linear reduction in the size, structure gets 100 times stronger because it is L raised to minus 1. So, what is the advantage here, that if you are scaling down all the system in terms of cantilever beam or something which is taking the weight of the part, then it is very important that if scale down smaller things will actually keep the weight very large. So, what is the example, that we have seen the smaller insect can survive a drop onto its leg from a height of many heights. If you fall down, any even lizard also, it is falling down from the bottom of a 2-3 floor building, still it will walk down very quickly and does not make any difference in that, but large animal cannot. If you do same thing with the elephant with respect to part, then at the bottom it will die. So, in this case, these are the example of a natural shape, but same thing will happen with the man-made things, that is when you design some beam element or something which is hanging on the top of that and some weight is on the top of it, at that time this particular scaling will important to understand how the strength to weight ratio will affect the design consideration. And coming to scaling effect on the spring constant, now we have, let us see those things. So, now there is a beam and beam it is a cantilever beam, and at the end free end we have applied a force F, and there is, because of that force F we will get some deflection here. So, maximum deflection occurs at the square beam edge. So, this is a square beam. So, this cross section is something like this. So, what is the equation? Deflection will be F into L cube divided by E into I. Now, F is the force which is here, length L is this L particular length, E is the modulus and I is the section modulus, and again the section modulus is the, this is the B by, and consider this is a square. So, this both dimensions are B. So, here that is why it is a B raised to 4 divided by 12. and stiffness of the beam given by the force divided by deflection, and if this is the equation, now what we are coming here. So, now if you put this equation, let us take this equation first. Now, here this is the parameter which is considered as a dimensional parameter, it directly connected with the length L, and I is also dimensional parameter, it has a connection with the cross section of the B. So, here it will be the L cube divided by L raised to 4. So, that means it will be L raised to minus 1. So, now consider this same thing, again a force is here, but delta, the deflection is at the denominator. So, this will be the L raised to minus 1, when it will come back on the top, that means K proportional to the L raised to 1. So, this is the formula. The smaller the beam, so now let us consider, now it is linearly scaling with that part. The smaller the beam, smaller the K value and more is the flexible. So, that is the advantage of going down into the dimensional scale. So, your beam become more and more flexible, because this beam, if you consider the MEMS or the micro electromechanical system, there are many applications where you use the cantilever beam as a sensing element. Now, if you take one example, let us take one example. So, this is the cantilever beam, and this is the considered as a capacitor. So, this is connected with the positive, this is connected as a negative, and this is the gap between the two plates. And now, you are adding one particular component, gas sensing component. Now, consider this example is a gas sensing sensor, gas sensor, that we want to detect the concentration of a particular gas in an environment. So, what we do that there are different elements available which will attract only particular type of gases. So, let us take one particular element, which is, this is the element gas attractive elements. Now, we are putting that thing, and now what will happen, this beam is very small. So, it is more flexible. So, what is going to happen with this, that when you are putting this whole system in environment, and it will start catching the gas molecule of a one particular component. So, this gas molecules will start sticking to the top surface. So, these are the gas molecules, it will start sticking to this part, and because of that what happened, that it is considering as a one of the parameter as a F parameter. So, when it is happening at that time, what will happen, that your F is increasing, you are loading this part because of that, and then your D will decrease. As the D will decrease, you will get a different capacitance here, and because of that you will sense that what is the concentration of that, because this particular beam, if you see here, it has a dimension of a B by B, and this is the top area on which. So, you know what is the area which is exposed to the gas. So, you know the area, you know how much the deflection. So, you can find out what is the concentration of the gas or that particular element in a particular environment. So, this is one of the examples. There are many examples like that which you can use as a sensing element or gas element or actuating element. So, stiffness to beam under self field, let us take this example also. Now, here what we are doing, that we are not putting any weight here. Let us see that what is the weight of the beam which will self sustain, that means up to which length or which weight you have to make a beam, so that it will not fall down under its self weight. So, now we are removing that particular F from here. Again the same equation, deflection is given by F L cube by E I, again the same thing here. Now, F will be reduced by the weight of the beam, because we have removed this weight and external loading, but we consider this beam weight itself behave as a weight. Again the beam weight is given by W, and we know that W is, that means we have considered the earlier case that this beam is a square beam, the dimensions both things are BB, and that is written here also. So, this is the W. Now, you are in terms of, in place of F you are putting W here, and if you are putting W here, then what will going to happen here? Now, W has a L cube, we have seen that it is rho into V, and already L cube is here. So, it will be L raised to 6, and at the denominator I is there, and I is connected with the B raised to 4. So, at the bottom it is L raised to 4. So, it will be L raised to 6 by L raised to 4, and that is the reason you are coming as a L raised to square, right. So, and we have the stiffness, that is force divided by deflection, and this will scale as like that. So, smaller beam behaves stiffer than the large one. So, now consider this K is here. So, your delta is here, delta will be a denominator. So, K is proportional to the K is L raised to minus 2. So, if you reduce the dimension, that means smaller beam behave more stiffer, that means if you reduce the dimension, your K will go up. So, if there is no any external loading, now consider this is it is just a beam only, and you want to see what is the total length or the total dimension of the beam you have to make in such a way that it will not fall down from that part. So, again you have to consider stiffness. So, it is scaling down as L raised to minus 2. So, smaller is the beam, more stiffer is the part. So, that is the way you can design the beam for the different system also. Now, strength of a cantilever beam. Now, let us consider strength, because why we are taking example of cantilever, because cantilever is a mechanical system, it can be used for the different design element when it is in assembling in different parts. So, maximum bending stress occur in the square beam at the constant. Same again we have taken the square beam, dimension is cross section is B by B. We are now putting one load at the free end, and dimension total length of the beam is L, and here is the modulus and the section modulus. So, now it is a sigma equal to m y divided by I. Now, sigma, this is the maximum bending point, m is the moment, and y is the B by 2, it is the distance from the outer surface to the neutral area, and I is the section modulus. And now, let us put I equal to B raised to 4 by 12. So, we are putting that, and m we are putting F into L. So, that is the load given here divided into L area. So, this is multiplied by this way. So, this m becomes FL, and I we are using from this equation, then we are putting it here in this case. So, what are the parameters which has length scale? So, this is the one length scale, this is another length scale, and this L has one more L scale, and this is also L square. So, now what is happening here, that here we are ending with a sigma is equal to 6a. So, this is going down and down, and this L has one parameter, B has one parameter. So, it will be L square and divided by L raised to 4. So, this is coming as a L square, and this B is coming as a L raised to 4, right. So, now if you consider sigma equal to 6 f divided by L scale, now we are considering everything in terms of the linear scale. So, this is the L raised to scale. So, your force will coupled as a 6 f into S. So, a shrinking of a 10 causes the 100-fold increase in the induced stress. Now, if you consider f as a constant, we are not looking at the f right now, but you consider the dimension only. So, if you shrink the dimension of 10 times, that means L equal to 1, it will come to the L raised to 10 times is L raised to 2. So, that is a L becomes 100. So, that is the reason that if you reduce the dimension, then your force will, because this whole thing is in denominator. So, your shrink or the total induced stress will be very high in this particular case. Now, what we want to do, so let us take in another way, then let us keep the induced stress to remain same. So, let us fix this particular thing. Now, if you want to keep this thing, then we have one other variable, that is called f, right. So, if you are keeping the stress value constant, then what will happen, the force acting on the beam must decrease as the square of the characteristic dimension. Why it is happening like that? So, now consider here only. So, it is a sigma equal to, let us ignore 6 right now, it is L raised to square. Right. Now, we want to keep this thing as a constant, and we do not want that this particular thing will pass through the bending stage, or it should not buckle like anything. So, if you want to do this thing, then this if you reduce the dimension L, now you are reducing the dimension by keeping this particular constant. What is the variable? Variable is f. So, to keep the sigma constant, whenever you are changing the dimension L, the reduction of the force should be also as a proportional to the L square, right. So, because now here f is equal to sigma into L square from this equation. So, keeping sigma constant, f should proportional to the L square. So, if the stress remain constant, the force acting on the beam must decrease, because this is on the opposite side, one is in denominator, one is in numerator. So, in that case, if you want to keep this constant, if you reducing the L, you have to reduce the f also, then only that proportionality will be maintained. So, here in this case we have can take this example in two ways, that what is the maximum shrinking or the maximum induced stress here in this case. So, that when you are scaling down, under that we let us keep the constant for induced stresses, but then let us work with the force, how much force we can apply onto the surface. So, this is way how it will work in the cases. Now, let us take some example of the fluid mechanics. Now, if you see the rate of volumetric flow of the fluid is given by one of example. So, this is the equation by Q equal to pi a raised to 4 delta P divided by 8 mu into L. So, this is the one of the tube, flow is coming from this direction, going out from that, length is L and the diameter is A, and the total pressure drop you can measure, or that whatever is coming is a delta P. So, now here what is the important part? The A is one of the parameter, this is the parameter, the dimensional parameter, this A. That is, right now we are discussing about the diameter only, we are not talking about the length. So, this Q is a proportional with a L raised to 4, whatever is the flow diameter per unit length. Let us consider this one as a per unit length. So, now what is going to happen? If you reduce the dimension 10 times only, then what will happen? The dimension, that means dimension L, that means A is the dimension. If you reduce the diameter or the radius 10 times, then what is going to happen? That your reduction in the volumetric flow will be the 10,000 times, because it is behaving as a L raised to 4. Let us keep the length constant. Length is also one of the parameter of a length scale, but let us not change the length right now, but let us see the how much flow we can pass out through this. So, reduction in this particular length scale, that means it is the diameter, what is going to happen? That volumetric flow will reduce with a 10,000 times. So, that is a problematic situation which we have to encounter in the microfluidics. Coming to the pressure drop, again the same formula we can use it, same example. Now, we are want to see that how much is the pressure drop between these two parts. So, pressure drop you can calculate from that earlier equation. So, that is divided, earlier we have found the P, delta P. So, from delta P you can find that, and final equation is coming as a 8 mu V average L divided by A square. Now, again L square, A square is coming as a denominator here, right. So, now consider pressure drop per unit length. Now, we are considering length, but length is not a one of the part of the length scale, but we are considering as unit length. So, now what is going to happen in this case, that it will be L A square. So, it will be L raised to minus 2, whatever is coming. So, here what is important part? So, 10 time reduction, now let us consider this is 10 time reduction in the radius will lead to 100 time increase in the pressure drop per unit length. So, if you reduce the diameter, your pressure drop will be very high. Pressure drop means the difference pressure as the inlet and the outlet pressure. So, what is the problem? Is the pressure driven pumping becomes very difficult here if you are working with the microfluidic. So, if you cannot just push the liquid from one location to the other location, so that you can get the, so you need some type of extra element or the external forces which will give, which will drive the force, but drive the liquid inside it. So, many examples available in this particular case, where people are putting some type of a piezo actuator here on the surface, and this tube is a flexible tube. And when this particular thing will, these are the piezo actuator, piezo actuating sheet. So, what will happen that this particular thing will create a one type of waves here, it will create a one type of pressing here. So, if you are providing one signal here, then it will contract it little bit and something like that. It is something like a squeezing a toothpaste. So, it will create a one type of waves here. So, because of that waves, the whatever liquid is, that liquid will be pressurized and it will move in this direction. So, that is the one of the way you can pressurize that thing externally, or you have to reduce, you have to work with the diameter, variable diameter of the air. So, that at the later stage your diameter will be very high. So, movement will be very easy in this case. So, let me finish this lecture here. We will continue with the same topic in the next class. Thank you very much.